Good day. My name is Shiva Jaggat, and my final year project is based on the investigation of household refrigerator with low global warming refrigerants. Firstly, I would like to begin with my introduction. The rationale behind my project is purely based on the fact that in the current state of the world, the concept of refrigeration is widely used in many aspects, such as refrigerators, air conditioning. However, the main refrigerant used in this process is chlorofluorocarbons, which is a common greenhouse gas which acts as a catalyst for global warming. Global warming is defined as the overall rise of temperature throughout the world, since the greenhouse gases exist in excess of normal levels, which lead to the heat entering the earth to be trapped, and over time, the heat waves will keep entering the atmosphere and not being able to leave. The CFCs cause chemical reactions to occur with the ozone layer, which is essentially the protective coating of the earth. However, these reactions are quite destructive and will ultimately deplete the ozone layer, which is a major negative. The purpose of the ozone layer is to prevent UV rays from entering the atmosphere, which ultimately will cause human conditions such as skin cancer and also impacts the plant growth, and finally it can cause cataracts in humans, which is a condition where vision is impaired. Basically, the general purpose of this project is to give an insight on several alternatives to avoid these harmful CFCs, as they impact all living life on Earth directly and indirectly. The Earth cannot function for much longer if the usage of CFCs are this high. Therefore, refrigeration needs to become more eco-friendly. Moving on to the statement of my problem. Currently, refrigeration is considered a multi-billion-dollar industry. This will impact the entire world's well-being, and therefore the usage of CFCs needs to be phased out over a duration of time. Countries that are considered the powerhouses of the world, such as China, Russia, and the USA, need to be targeted initially, as they lead the world's consumption, where currently the consumption is approximately 400,000 tons, which is a figure which was given by the UNICEF between the years 2014 to 2018. The aims and objective of my project are as follows: to identify a list of alternative refrigerants to CFCs, to identify the distinguished properties of each alternative along with the pros and cons of each. Thirdly, to compare and contrast between alternatives and the CFC refrigerants, and ultimately to choose the best alternative to CFCs from the list which was generated above, and to give suitable supporting information to persuade the readers as well. The methodology. In my methodology, I would like to discuss information which was gathered by online research as well as a survey. However, as discussed further on in the project, the survey was no longer carried forward with. Because it was concluded that the information gathered by the survey would be inconclusive to this study. The method of study. The purpose of conducting this study was to research and determine valid replacements for CFCs in the refrigeration industry. Online resources are important in gathering information for the proposal, as it was the primary source of information across numerous countries. In the study, I carried out an experiment based on simulation, which was carried out on the Cycle DHX software, which will determine the coefficient of performance and temperature glide when given the relevant values of the refrigerator. The materials required to carry out this experiment was the specification booklet of the specific air conditioner, which was a brand called Carrier, as well as the Cycle DHX software, which was the software carried out for the simulation. As you can see on the slide, this is the basic. Moving on to the method of this experiment. Moving on to the analysis of data. For this research project, the analysis was done between four refrigerants, where R1314A is the refrigerant being the one trying to be replaced, and then the R404A, the R449A, and the R513A are the refrigerants being analyzed to replace this R1314A refrigerant. The simulation done on these four refrigerants was the main part of this experiment, as this was the part where they determined the coefficient of performance and the temperature glide under predetermined conditions to suit the appropriate atmosphere and environment. Once this program was running, four different results were generated, which will be shown in the following slides. As we can see in this slide, the results for the coefficient of performance are given. It can be seen that R452A has the highest coefficient of performance, and the R1314A has the lowest coefficient of performance. This basically means that the R452A will be the more efficient refrigerant, since coefficient of performance gives a relative description of the efficiency of this refrigerant. Therefore, the higher the coefficient of performance is the more efficient. Moving on to temperature glide. As we can see, there are a few similarities between R1314A, R513A, and R452A. Basically, temperature glide is the difference between the beginning of a temperature phase and the ending of a temperature phase. So basically, this is the difference between the initial temperature and the final temperature of a specific temperature phase. Therefore, the lower the temperature glide across the evaporator and condenser will be, the more efficient the system will be, since the temperature difference between the beginning of the phase and end of the phase will be very low. Therefore, between having a warm fluid to having a cool fluid, they will have minimal temperature. Therefore, it can be seen that the R1314A is quite comparable to the R513A and the R452A, since there is a uniform distribution of temperature in the evaporator and the condenser. Moving on to the global warming potential and the ozone depletion potential. Basically, global warming potential is the measure of the ability of the refrigerant to impact the environment, while the ozone depletion potential is the ability of the refrigerant to impact the ozone layer. Therefore, we will like the global warming potential to be as low as possible and the ozone depletion potential to be 0 or as close to 0. Moving on to the selection criteria which was given in determining the ideal refrigerant out of the list provided. Firstly, I would like to determine if the specific refrigerant can be potentially be flammable or toxic in any way to humans. Moving on, the second criteria will be determining if the coefficient of performance is the highest, and if this is the case, I can move forward to the third step, where I will determine if the global warming potential is the lowest. And if so, I can move forward to the fourth, where I determine if the ozone depletion potential is 0. In the fifth step, I determine if the temperature glide is lowest. And in the final step, I will determine which refrigerant matched all of the previous criteria. As we can see here in this slide, this was the calculation used to determine the volumetric efficiency, which was ultimately 0.915. Moving on to my discussion. In the discussion, I discussed the chemical stability and chemical composition, coefficient of performance, global warming potential, ozone depletion potential, and temperature glide. This was all done in depth. Firstly, chemical composition and chemical stability. All of these refrigerants are blends of pre-existing refrigerants, where scientists and relevant engineers mix these refrigerants in order to get the ultimate goal of having ideal efficiency and minimal environmental and human impacts. Therefore, in this slide we can see the refrigerant blends of the four choices to replace R131.4a. As we can see, two of these refrigerants contain R131.4a, which is a major turnoff since this is the refrigerant which we are trying to avoid. Therefore, this automatically places two refrigerants in selection. However, R452A is the more desirable refrigerant as it has the best blend. The coefficient of performance is the second criteria which was investigated. Basically, as previously stated, the higher the coefficient of performance is the more efficient this refrigerant will be. Therefore, the obvious choice using this bar graph will be the R452A. And it is much higher than all the other choices, including the one that is trying to be replaced, which is R131.4a. Thirdly, the global warming potential and ozone depletion potential. The global warming potential needs to be as low as possible, and the ozone depletion potential needs to be zero or as close to zero as we can get. Therefore, once again, the obvious choice will be the R452A, since the R513A has been previously banned across all countries at the beginning of 2020. Moving on to temperature glide. Temperature glide is the difference between the initial and final temperatures within a phase change. Once the values are collectively low, it will be desirable as it shows a phase change doesn't take long. Therefore, as we can see, R131.4a, R513a, and R452a all has the same temperature glides, and it is also uniform between the evaporator and condenser. So, this would be the obvious choice to choose the R452A, since the coefficient of performance, the ozone depletion potential, the global warming potential are all in favor. Therefore, R452A will be the chosen refrigerant using the selection criteria. Now, to end off my presentation, the conclusion will include these points: my independent observation, justifying the process which I took, proof that objectives have been completed, and recommendations for future work. To begin with, independent observations. During the course of this year-long project, many different portions of the study expanded my basic knowledge on refrigeration systems and the intricate details around the whole concept of making refrigerants as green as possible. Growing up as an aspiring engineer, I was always accustomed to R131.4a being used in domestic refrigeration, and was also accustomed to the constant warnings about the harmful effects of R131.4a and CFC refrigerants. I took these claims for granted until recently, when this research project gave me an insight on the many different refrigerants which have not been heavily researched that can replace these harmful refrigerants and aid in preserving the environment for future generations. Additionally, the research done on the alternative refrigerants showed me how different properties such as coefficient of performance, temperature glide, ozone depletion potential, and global warming potential can be so vital in the selection and implementation of refrigerants into domestication refrigeration systems. A greater insight into this topic showed me that the slightest of percentage inefficiencies can go such a long way into the future with regards to electrical bills and the general lifetime of the equipment. This project also diversified my knowledge on refrigerants, and the simulation process showed me the thinking process which is required by engineers when designing these systems, and also making it as efficient as possible. Finally, I discovered that refrigerants are perfected in manufacturing by adding various refrigerants together in order to obtain desirable outcomes, such as being non-flammable, non-toxic together, with a favorable thermodynamic property, such as coefficient of performance. At the end, it was concluded that R452A was the chosen and most appropriate refrigerant, since it satisfied all criterions which were previously discussed in the analysis of data. It was a strong contender to replace R13148 as a domestic refrigerant based on my research and results from the simulation, together with applying this process to the selection of criteria. Moving on to the justification of the process taken. In this project, the process which I took in doing research was solely based on simulation. The simulation would have replicated a traditional modern air conditioner system, which is commonly used domestically. The model of this air conditioner is the Carrier RAS13N3KCV, which is the indoor version. This was chosen based on the fact that it's commonly sold unit, so it may capture a large percentage of this population. The refrigerants which were chosen are based on the fact that they are not mainstream and not heavily researched. Therefore, the number of articles were limited as compared to mainstream and common refrigerants such as R13148. The parameters which were focused on are a vital part of determining the efficiency of the system. Therefore, to determine which of these refrigerants could effectively replace R13148 as a domestic refrigerant. The software which was used was chosen based on a previous paper which I have read in the aid of this project. It stood out for me as compared to the others such as Transref, VapePsych, and Coil Designer. It provided a simple layout for data entry and provided all the necessary data outputs such as the coefficient performance and the required graphs in addition to the temperature glide. This is also a reputable software which was used by many research papers which were also used in the same direction as my study which was conducted. At the end, the required information was gathered and conclusions could have been drawn based on the simulation results. Moving on to my third point, which discusses the proof that objectives has been completed. So, the objectives which were given at the beginning of this project were to identify a list of alternative refrigerants to CFCs, to identify the distinguished properties of each alternative along with the pros and cons of each, to compare and contrast between alternatives and CFC refrigerants, and finally, to choose the best alternatives to CFCs from the list which was generated. From the list above, it can be seen that throughout this project, a list was generated where it was established that R404A, R440A, R513A, and R452A would all be examined as possible replacements for R13148. For the second point, it is seen that the coefficient of performance, temperature glide, global warming potential, ozone depletion potential, and the chemical properties were all used to distinguish each of these refrigerants in order to eliminate the refrigerants which will definitely not be used. Also, to cover the third point, each of these refrigerants were also clearly discussed in detail using different parameters to show why each would be suited or not be suited for the purpose being examined. And finally, it was concluded that the R452A refrigerant would be the choice after research was done and suitable reasons were given in the conclusion, as well as in the discussion. Moving on to recommendations for future work. As known in research, there would always be something that will be overlooked, or the study being outdated after a few months or years due to the evolution within the industry. Therefore, the recommendations for future work will be as follows. To use various software in order to justify the information if time permits. Secondly, to attempt physical experimental data, as it was not possible in my study due to the current situation of being in a pandemic. Thirdly, to expand the scope of the study and use other refrigerants which may be present in the future markets in order to see if there's something that will add to the betterment of the refrigeration industry. Lastly, instead of doing the research project on domestic refrigeration. Lastly, instead of doing research on domestic refrigeration units, attempt to research refrigerants for larger scale operations. Additionally, some limitations of the project are: due to us being in a pandemic, simulation needed to be done and experiments could not be done to justify the simulation results. Therefore, this was the only source of obtaining results. Lastly, due to the simulation being based on ideal data, condition may change in the actual environment where the refrigeration unit is placed, and results may vary and deviate from data presented in this experiment. And this brings me to the end of my presentation. Thank you for your time.